Hello and welcome back to Introduction to Number Theory. In this video, we will see how Euclidean algorithm leads to the greatest common divisor. Well, first, let me write this down. So we will need Euclidean algorithm. And for this purpose, let us consider, say, A and B that belong to a ring. And let's divide A to B with remainder. A is equal to B Q1 plus R1. Where, of course, R1 is the remainder. Then we know that B comes here and R1 comes here, Q2 plus R2. We have a new remainder. Then R1 comes here and R2 comes here, Q3 plus new remainder, and so on, until one of the remainders occurs to be zero. We know for sure that this will happen sooner or later. Well, let's suppose that it happened when Rk minus 1 was equal to Rk multiplied by Q, well, obviously K plus 1, plus 0. Well, this was the moment when the remainder became equal to 0. And now let's study the connection between Euclidean algorithm and the greatest common divisor. We'll need a lemma for that. It's a small lemma, which states that if x is equal to y, say delta plus z, well, it's a bit unusual set of variables. I was eager to underline that x, y, and z are the variables we are interested in, and delta is just some element of the ring. We don't care about it. So if this equality holds, then the greatest common divisor of x and y is equal to the greatest common divisor of y and z. Well, indeed, just consider a pair of elements, x and y, just a pair of elements, and another pair of elements, y and z. Well, if x and y have some common divisor, d, then x is divisible by t, y is divisible by t, so z is also divisible by t. So y and z are both divisible by t. At the same time, if y and z are both divisible by t, so this is divisible, all this is divisible, so x is also divisible by t. This means that these two pairs of elements have not only equal greatest common divisors, they simply have equal sets of common divisors. So any common divisor of this pair is immediately the common divisor of this pair and the other way around. Now we will return to our Euclidean algorithm, and this looks very much like a step, just a general step in the Euclidean algorithm. So, stepping towards the greatest common divisor of A and B, we can say that according to the lemma, the greatest common divisor of A and B is equal to the greatest common divisor of B and R1. Okay, the greatest common divisor of B and R1 is equal to the greatest common divisor of R1 and R2. Okay, the greatest common divisor of R1 and R2 is equal to the greatest common divisor of R2 and R3. Well, we do understand that these are just the same, and also these, and also, and so on. So finally, in the end, we will have that the greatest common divisor of Rk minus 1 and Rk is equal to the greatest common divisor of Rk and 0, and the greatest common divisor of something and 0 is of course equal to something, because 0 is divisible by any element. So this is equal to Rk, which finally proves that the greatest common divisor of A and B is actually equal to Rk, since all these GCDs are equal.